Okay, so here is the final review. Summer 2015. Tomorrow is your final exam day. Now I have to act professional. See. All right, the speed of waves, that's obviously our first chapter. Speed of waves is, of course, the product of frequency and wavelength. But remember that frequency never changes when it goes from one material into another. It's always wavelength and speed that change. Wavelength changes, speed changes. Obviously, if the wavelength decreases, then the speed also decreases. Frequency is a constant. Remember that. Another equation for velocity or speed of waves is square root ft by mu, where ft is the tension, and tension has got to be in newtons. So if the mass is given, you have to change it into kilograms, multiply it with 9.8, you get the tension. And mu is mass of 1 meter of the string. Mass of 1 meter of the string. So if you're given a mass like 45 grams and let's say the length of the string is given as 2 meters, you don't do 45 by 2 because you got to change grams into kilograms and divide by the length, so you will get mass of 1 meter. That's what you mean by mu. It's called linear density. So if you see a word linear density, that's mu. But there's also another way of finding mu. It's pi r squared times rho, where r is the radius and rho is the density of the material. That's topic number 1, question 1. I'm not saying the first question. There's one question based on just this. So try to study everything about this. Think properly about what's mu, Second one is about beats. What is beats? Beats is produced due to the superimposition of two frequencies that are slightly different from each other, isn't it? And beat frequency will be the difference in frequencies. So when I say beat frequency, it means number of beats produced in 1 second. And what do you mean by one beat? One beat is one maxima and one minima taken together. So you got to understand that. One beat is one maxima and one minima. That's one beat. And it's always equal to the difference in frequencies between the two that are being superposed. Right. On the same slide, I decided to write about electric field. Electric field is defined as, can somebody define electric field? So it's not monotonous. Electric field. Force acting on. What's the standard? Positive or negative? Okay. Electric field is the force acting on +1 coulombs. From that you get the equation F is equal to Q times E, where E is the electric field and Q is any charge that is kept there. So that gives you the force. Right? Force acting on a charge Q coulombs kept in an electric field of intensity E is F is QE. From there, can you find the acceleration? Of course, acceleration is force divided by mass, right? From there, can you find the displacement? Yeah, if necessary, go back to the kinematic equations and find the displacement or the time or whatever. What is Gauss' law? Gauss's law. The total electric flux passing through a closed surface. Is that an imaginary surface or a real surface? It's an imaginary surface. The total electric flux passing through an imaginary closed surface is equal to, somebody complete it, 1 by epsilon naught times the total charge inside the surface. Now, the term inside the surface is very important. So if you're given a diagram with so many charges inside and some outside, you only consider those charges that are inside. Be careful. And if it's a positive charge, the flux goes outwards. If it's a negative charge, the flux comes inwards. So if you have both positive and negative inside the closed surface, what are you going to do? Let's say it's 5 positive and 3 negative. So you have to take 2 positive, right? Easy. Come on now. And so the total flux will be outwards. If the net is positive, it will be outwards. If the net is negative, it will be inwards. So that is Gauss' law. So total flux is 1 by epsilon naught times the total charge enclosed by the surface. Okay, again, it should be a closed surface. It's an imaginary surface. Remember that. What is the formula for kinetic energy of a charged particle accelerated through a voltage? I know the formula for kinetic energy is, everybody knows that, 1/2 times mass times velocity squared. But I'm asking you, if I give you a charge q coulombs and say it's accelerated through a certain voltage, what is its kinetic energy? That's it, VQ. Therefore, can't you set 1/2 mv squared is equal to VQ? Right, important point. So kinetic energy of any charged particle is 1/2 mv squared, but that can be set equal to QV. Do not cancel the, because one is the velocity and the other is the, all right. Remember all this. Just remember. Physics is easy. You don't believe me, I know. Capacitance, it's a favorite. Now, did you notice that there's no question on Doppler effect? Because I'd mentioned that yesterday, and I said no. Because you had 2 or 3 questions on Doppler effect on exam number 1. So I said, yeah, that's taken care of. So nothing on Doppler effect. So capacitance. How do you define capacitance? It's the ratio of the charge to the voltage. Is capacitance a constant? Yes. Capacitance depends only on the geometry of the capacitor. It depends on the area of the plates, the distance between the plates, and the dielectric between the plates, isn't it? That's all. So if you apply 2 volt or you apply 10 volt, the charge on the capacitor is going to change, but its capacitance is constant. I'm also trying to tackle some conceptual questions, although it's not easy, okay? So capacitance is given by this formula, K epsilon naught A by D. What's K? Dielectric constant. What does that mean? What does that mean? It means how many times the permittivity of that material is compared to that of air. So if you say it's 5, that means it has permittivity 5 times that of air. So you have to understand that, because it might be a sentence. It may not be dielectric constant. It might be, you know, what I can do. So it might be like, hey, it has a permittivity that's 7 times that of, and then people are like, is that the dielectric constant? How was electric potential defined? What's the most basic definition of potential? Not voltage, electric potential. Huh?
The ability to do work.
Yeah, it's connected to work. So how is it defined? It's work over charge. It's work over charge. That's the most basic definition of electric potential. What's the energy of a charged capacitor? There are 3 formulas, remember? And you have to use it in context. One is 1/2 times capacitance times voltage squared, which is the most basic one. Then you have 1/2 times Q times the voltage. And then you have Q squared by 2C. So you have 3, but you have to know what's given in the problem and use the formula in context. That's all I can say. You can't just pick and grab. You know, I know everybody likes the first one. Doesn't mean that you can use it always. You have to read the question and use what you have to. Now, instead of saying calculate the energy of a charged capacitor, can I say, what's the work done in charging a capacitor? Will it be the same?
It's the difference in potential.
No, will it be the same if I ask, what's the work done in charging a capacitor to such and such voltage? All you have to do is find the energy of the capacitor. Remember that? I just looked at the exam and I made this. So you know what I'm trying to say. If I say something, it's very important. And I didn't do it yesterday evening. I did it in the morning, so it's fresh in my head. It's like giving you the questions. Current. Microscopic current is NAVDE. Okay, let's go through the terms one by one. What's N? Perfect. N is the number of free electrons in 1 meter cube. Students tend to miss that. Don't. It's not the total number of free electrons. It's the number of free electrons in 1 meter cube. A, the area of cross-section. Most of the time it will be circular, right? So it will be pi r squared. All right. What's that? VD. Drift velocity. I still remember. Is drift velocity small or large? Small. Extremely small. Okay. Keep that in mind. And E is the electronic charge. Charge of the electron. What do you mean by current density? Current density is current divided by area of cross section. That's all. It's represented by J, and J is a vector. I don't remember if I put a vector symbol over that, or maybe I didn't even write the symbol. Maybe I did, but I forgot to put the symbol over it. It's a vector. So what about current? Is that a vector or a scalar? All right, that's why I did say that. So when you have the formula, it's going to be everything except the A, because the A will get cancelled. Power, again, use it in context, because there are 3 formulas for electric power. One is the product of voltage and current, right? The other is I squared times the resistance. And then it's just similar to that, V squared by the resistance. So there are 3. Use it in context. Read the question. And those are the 3 formulas for electric power. All right. DC circuits. There's one question on Kirchhoff's laws. So I thought I should remind you about it. I just drew a simple circuit like that, changed it a little bit. So let's take one last minute to look at whether you understood. Okay, I'm going to change that. I included resistances because I thought this is too simple. All right, so if there is a resistance there and here, and label the currents as I1, I2, I3, what is Kirchhoff's first law as applied to this junction? At this junction, what's Kirchhoff's first law?
Current entering is the same as the current leaving?
Yeah, the total current entering must be equal to the total currents leaving. But mathematically, what do you get there? I3 and I2 are coming in, isn't it?
I2 plus I3 plus I1.
That's it. I2 plus I3 is equal to I1. I think everybody knows that part, but a few are confused about the second law. I don't even know why. I just have time to apply it to one of the circuits, so I labeled that. I can't remember which one. So let me wait. All right, so let's call this A, B, C, D, A. All right, so we're looking at A, B, C, D, A. Going back to A to show that it's a closed network, right? And if we start from here, you're going this way. Is that positive or negative? Positive. So it'll be plus E1. And since you're going in the direction of the current, it's going to be minus I3R3, minus I1R1, minus I1R2, right? Yes. Is equal to 0. That's it. Most 90% of you are very clear about that. I don't even know whether I wrote the right thing. Let's check. And then once you apply this to 1 or 2, you just solve it. I don't care how you solve it. Use your calculators. Okay, I was worried if I had written that term. I did. Okay, so that's perfect. That's clear, isn't it? Kirchhoff's laws. Simple. Force on a charged particle in a magnetic field. Somebody give me the formula. What's the formula for force on a charged particle in a magnetic field? That's where we had all this dance with the right hand. Remember that? Okay, let's look at the right hand, although I've not drawn it and all that. Okay, this is the direction of current. When you bend it, magnetic field, and that's the direction of no confusion. Why should there be confusion? And some are confused about this one. That's entirely different, isn't it? What is that used for? That's used to find the direction of the magnetic field due to a current. You hold it with the thumb in the direction of the current, and this will give you the magnetic field. Remember, I told you that it should be perpendicular to the line joining the conductor to the point. So if the point is here, You have to imagine a line, and then it should be perpendicular to that. If it's here, it's going to be that way. It's clear about that, right? So I think we clarified that. Coming back to this, what's the formula for force on a charge in a magnetic field? That's Q V cross B. That's where you have the cross product, the IJK stuff, and most of you are really good at that, so I thought I should have one problem in that. Really. I looked at the past and said, most of you are really good on that, so there's one question on that. So F is Q V cross B. And what will be the direction of the force? It will be perpendicular to the plane containing the velocity and the magnetic field. Right? Okay. And then magnetic field due to a straight conductor. Magnetic field due to a straight conductor. What's that? Mu naught I by 2 pi d. Mu naught I by 2 pi d, where I is the current flowing, d is the distance of the point. Are you with me on what I'm saying? Is this sounding like a dream? No, okay. What about the form for magnetic field due to a solenoid? Due to a solenoid. That's one of the easiest formulas. Mu naught Ni. Just mu naught Ni. But you got to be careful. What's N there? Number of turns in 1 meter. So that's why I wrote it on the right side and said if it's caps N, it's total number of turns divided by the total length of the solenoid, right? So total length, yeah. That's a magnetic field due to a solenoid. I like this chapter on alternating currents. Inductive reactance represented by XL, right? What's XL? 2 pi F times the inductance. As the frequency increases, the inductive reactance also increases. The opposite is true for a capacitance. Capacitive reactance is 1 by 2 pi Fc, which means when the frequency increases, the capacitive reactance decreases. So which one can be used to block a DC capacitor? When frequency is 0 for DC, capacitive reactance becomes infinite, isn't it? Right? Simple. What's the impedance of an LRC circuit? All three in series with each other. What do you get? Square root R squared plus XL minus XC whole squared. You don't even need the formula chart by now. Do you, right? I'm going to give it to you. But do you realize that? That's how much I have pushed you. You remember this, it's stuck in your head forever. You're never going to get rid of it. And tan phi is XL minus XC by R. And we did labs on this, isn't it? So it should be really perfect now in your head. You should know about resonance. I think there's one conceptual question on resonance. Does resonance depend on the value of the resistance? Resonance. What's the formula for resonant frequency? The formula for resonant frequency, come on. F is equal to 1 by 2 pi root L times C. Do you see resistance in it? So, what part does resistance play?
The value of the peak,
Right. It shows you how high or how low the peak would be. It doesn't shift it along the x-axis, but it shifts it along the y-axis. Come on. Because on the x-axis you have frequency, right? And frequency depends only on the values of the inductance and the capacitance. What do you have on the y-axis? Current. Doesn't that depend on the resistance? Yeah. So what would be the maximum value of current? At resonance, the maximum value of current would be, whatever, I is equal to the applied voltage divided by, what's the total impedance at resonance? R. Thanks. I'm just trying to throw some light on the concepts, but, okay, it can't be done in 1 or 2 hours. No. This is your graveyard, right? Exam 4. All right. One equation, 1 by f is 1 by do plus 1 by di. Everybody knows that. Do is the object distance, di is the image distance, f is the focal length. But I do not know what the confusion is about. Before I go there, there are two formulas for magnification. One is magnification is hi by ho, and the other is minus di by do. All right. The whole thing in a nutshell, the convex lens is similar to a concave. All right. And both of them have a real focus. Therefore, both of them have a positive focal length. You see what I'm saying? And therefore, both of them can produce both a real image and a virtual image. It's the nutshell. Which are the both that I'm talking about? Convex lens, concave mirror. Both have real focus. Both have positive focal length. And both can produce real as well as virtual images. When do they produce a virtual image? When the object is really close, isn't it? For a concave mirror, it should be inside the focus. Same thing for a convex lens. It should be inside the focus. Come on. Is that easy to remember? Now on the other side, you have the other two. What are they? Concave lens and convex mirror. Both of them have a virtual focus. Therefore, their focal length is negative. So as soon as in a problem you see a convex mirror, blah, 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 has a focal length, whatever, you take it as negative. Same thing with a concave lens. If I say the focal length of a concave lens is 15 centimeter, you're going to take it as minus 15 centimeter. You can't take it as positive. And both of them can only produce virtual image. And another point is all virtual images are upright. All real images are inverted. Come on now. So it's so easy. The first set, what is that? Convex lens and concave mirror, they are both converging. The second set, what's that? The concave lens and the convex mirror, both are diverging. Done. It's nothing as easy as physics. Just summarize, you got it. And then you have these cheap formulas into which you substitute simple numbers and calculate with a proper head, that's thinking about what you're doing, and your grades will fly, I'm telling. And I wanted to. That's a summary of what I told you just now. I like interference, especially at thin films. Now, these are the two formulas that are important, and we have used it several times, right? Tan theta is y by, what's y? Distance on the screen from the center. What's L? Distance of the slits from the screen. Now, tan theta. And on the other side, we have sine theta is equal to, that's not right, sine theta should be m lambda by small d, right? Okay. Where, what's d? Small d. Distance between the slits, and lambda is the wavelength, and m is the order of the spectrum. For the central one, m is 0. All right, easy. That's what y and L are. That's theta. That's all I did. Did you understand that? And then when you get to thin films, people just make a lot of noise. I don't know why. So I said, let me spend 2 minutes on that. Thin films. The last chance. All right. The additional path difference is created when reflection takes place if it's trying to go from a less dense to a more dense. Let me repeat that again. The additional path difference is created when reflection happens if it's trying to go from less dense to more dense. Is that clear? All right. Okay. So there are 3 materials there. You have air, oil, and water, which I've used continuously, and I've taken the refractive indices to be just very close, but at least, okay, I changed it. Okay. I thought if it's too close, then you might say something else. Does this reflection happen as it's trying to go from less dense to more dense?
Yes.
It's trying to go from air into oil, isn't it? Yeah. Does this reflection happen when it's trying to go from less dense to more dense?
Yes.
Yeah. So in both cases, you got to add lambda by 2, which in effect means you don't add it, correct?
Yeah.
Agreed?
Yeah.
Therefore, what's the path difference in this case? 2nt. The geometrical path difference is 2t, approximately. But why do you have to multiply with n? Because the path in the material is equal to path in air multiplied by its refractive index. Okay. So the condition for brightness is 2nt is equal to m lambda. Okay, there I was just trying to explain it, whatever I told you right now. Now, if the additional path happens to the first one, the additional path happens to the first one and not to the second one, all right? Then what will you do? Then this will be 2nt minus lambda by 2. If the additional path happens to the second one and not to the first one, what do? It will be 2nt plus lambda by 2 is equal to m lambda. I can't make it clearer than this. I hope you're not cramming. You understand why, right? Because I won't give these tricks in the beginning. If I do that, then you'll just cram that without knowing why. But we went through the struggle now. Now you know why. And now you can have the tricks. Not the other way around. See, that's one of the major mistakes they have. You just give them the tricks. Why? Don't know. Last, but not the least, we did this yesterday. And you've never been questioned. So there are two problems from this chapter. At least 2 concept questions from this chapter. At least 2. I think there are 3. I can't remember. Focus on these 4 formulas. Time dilation, length contraction, relativistic momentum, and this. This is a major thing. But you understand you have to set it up in such a way that ux is always what you're trying to find. Last time, what's ux? You had, draw on there. You had s prime, and you had something moving at velocity ux prime. Okay. What's ux prime? The velocity of that object as compared to s prime. And s prime is already moving relative to s. With what velocity? Right. So what you're trying to find is or should be the velocity of that object with respect to s. So you have to set it up that way, Most of the time it will be s prime could be taken as the earth, and the rockets could be taken as the other two. But sometimes you have to switch. I'm telling you. On one of the quiz questions that I did in the morning, I had to switch. I started saying, as usual, we will take the earth as the s prime, and then I saw that no, we can't, because the question is asked in that way, So pay special attention to that problem on the quiz, which is already on YouTube. So that's your review. Those are your questions. Thank you. It took us 30 minutes for the review.